Okay, the next very useful theorem to determine if a particular infinite series is converging or diverging is called comparison test. So what we do here, so let's actually read this carefully. Suppose that we know that the sigma Bn, the infinite series, is convergent, and Bn is always, for every every n, Bn is always bigger than An. Then the theorem tells us that An is also convergent. So this is almost intuitive, right? So if you have, right, let's call this S, okay, where n is equal to 1 to infinity. So this converges to a particular number. Okay, and let's consider the partial sum. So let's call it T. That's partial sum of this. So Tn is essentially, we're going up from n is equal to 1 to n. Let me use I. I is equal to 1 to n for An. And Tn is increasing, right? It's an increasing function because we're always adding the next An. So for example, Tn plus 1 is Tn, and we're adding the n plus 1 term. But no matter how much we add, right? No matter how much we add, right? So it's gonna have to be less than the c, right? So it's constantly increasing, and it's gonna have to be less than c as n approaches to infinity. So this type of sequence where it's constantly increasing, we call that a monotonic sequence. Okay, so we encounter this in the sequence section, monotonic, and we know that every monotonic sequence, right, with an upper bound, it's convergent. Okay, every monotonic sequence that's increasing and its upper bound. Okay, so in layman language, just means if the function is if the sequence is increasing, the sum is increasing, but then there's an upper bound, then it has to converge. Okay, you cannot, and it has to continue to increase, right? So it has to converge to this value c. Okay, so similarly, if you have a series that's divergent, so it's approaching infinity, and we have An that's bigger than this one, of course this will also diverge. Okay, so it's like you have, a series where Bn is bigger than An, and this is going to infinity. So this has to be something bigger than infinity, right? So we can't define it in any way other than say it's also diverging. Okay, so the more important thing is how do we apply this theorem. So let's do an example. Okay, suppose we have this example here. Now let's let that be An. Now if I let Bn be 1 over 3 to the power of n, clearly Bn is bigger than An, right? Because if you add 1, right, it makes the overall fraction smaller. Okay, so this is less than Bn. But we know that 1 over 3 to the power of n, right, this is a infinite geometric series with a ratio of 1 over 3. This is going to converge. Okay, so that's going to converge. Therefore, by comparison test, we know that the infinite sum of this also has to converge. Okay, so this converges to a particular number k. You know that this has to be less than k, so it's going to converge to that particular number.